Good evening. Welcome you to this fourth problem solving session for the NPTEL course Gasdynamics Fundamentals and Application. So in this session, we'll be discussing mainly about normal shocks, numericals on normal shocks, and also we'll see how we can use the gas tables to solve the numericals. Okay. So in the last session we have discussed the stagnation properties and star properties, and how it acts an important reference point in analyzing canonical quasi 1D flows. Okay, and we have seen how that when the flow is adiabatic, you can always say that stagnation temperature stays constant. Otherwise, if there is heat addition, the stagnation temperature increases. If there is heat loss, the stagnation temperature decreases. And if the flow is adiabatic, at the same time it's irreversible. If the flow is adiabatic and reversible, which means it's isentropic, then we have seen that the total pressure stays constant. But if the flow is adiabatic but irreversible, which means that is because of flow irreversibility, there is entropy generation or increase in entropy in the flow. In those cases, we have seen that the total pressure decreases. Okay, so these are the major variations in stagnation properties we have seen. Okay, so today let's start with the discussion on normal shocks. Okay, before that, if you have any questions or doubt, anything, you can ask me. Okay, I guess things fine. So let's begin. Okay, so first let me introduce this to the concept of gas tables. Okay, so and how, so today we'll be using these gas tables to solve most of the problems. Okay, so as we have seen these ratios of, so the first, let's say the isentropic stagnation properties, this T by T0, P by P0, right? This ratio of static properties to stagnation properties, all this we have seen, this is a function of Mach number and gamma, right? This is a Mach, this is also a function of Mach number and gamma, right? Now we know mostly we have seen in the problems we deal with, our working fluid is air. So for air we know that gamma is equal to 1.4. In those cases, these ratios become just a function of Mach number, right? So so since these are like varies Mach number, these gas tables are available. So this gas table is taken from this book, Fundamentals of Gas Dynamics by Zucker and Biblards. Okay, so I have taken this from the appendix here. So you have seen, if the table title is said isentropic flow properties corresponding to gamma equals to 1.4. Okay, so if it's, as I said, if gamma is held constant, this and the ratios becomes a function of just Mach number. Okay, so you see there, the function of Mach number, different values are given. So first is P by PT. So here we generally represent total or stagnation condition as P naught. So here it is represented by PT. So just note the change in notation. So first we have ratio of static to stagnation pressure. Next we have ratio of static temperature to stagnation temperature, and then and the fourth column we have area ratio. So if the A star, so A star is the area, let's say we have a flow at a given Mach number m, at where the flow area is A. So A star is the area at which the flow Mach number will become 1, right, or sonic, or the flow velocity will become sonic if the flow is isentropic. Okay, so we get that area ratio, and there is another parameter called PA by P naught A star. Okay, so remember, these are isentropic flow parameters. Okay, so this is this, you can use this when the flow is isentropic. Okay, and then nu is a parameter. We'll come into discuss this what is mu later in the course when we start discussing about expansion fans. And mu is, as you know, is the Mach angle. So this, and we know that Mach angle is defined only when Mach number is greater than equal to 1. So you see there, this is So only when that values are given only for Mach numbers greater than 1. Okay, so so this is how the isentropic flow parameters for uh, gas a gas table for isentropic flow parameters look like. Okay, now let's just solve a simple problem using that. Okay, so first we have here the given an aircraft with a turbojet engine is flying with is cruising at a Mach number of 0.8 and an altitude of 10,000 meter. Okay, so and the ambient conditions are Pa by is 0.265 bar and a temperature of 223 Kelvin. We have to find the stagnation conditions at the inlet of the intake. Okay, so we know we can use the formula, like let's say we need to find out stagnation temperature. We can use this formula 1 plus gamma minus 1 by 2 m square. Okay, right. So now instead, if you want to just use the gas tables, so if you see from gas table and use this, like for Mach number 0.8, we see that Ta by T0A, ratio of static to stagnation temperature, this should be 0.88652, and static pressure to stagnation pressure, that will be equal to 0.65602. Okay, so now you can compute this and directly find the values. Okay, so can anyone of you and one more thing, I have in the chat box I have provided a link, drive link, where this PDF of this gas table is uploaded. Okay, so you guys can download it and use it for your for the problems we'll do today, and also your practice problems and assignment problems if you wish. Okay, so can anyone just compute and tell me the values of the stagnation pressure T0A and P0A? Right, so thank you Apurv, we will get 251.88 Kelvin, and the pressure 0.265 divided by 0.652. Okay, rating something 0.404 bar. Okay, all right, so this is how, so like for simpler problems, like when you go to more complicated problems, so you can like use the gas tables directly to get the answers quickly. Okay, it will save you a lot of calculation time, because the expressions get complicated as well. When you will see, like for normal shocks the expression gets complicated, so using like the gas tables in case of normal shock problems is more useful. Okay, all right, so next part of the problem. So the hot gases leave the turbine and enter the nozzle at a total temperature of 992.3 Kelvin and a total pressure of 1.284 bar. Stations 4 and 5 represent the inlet and exit of the nozzle respectively. Okay, and it says that the nozzle operates isentropically and is choked, which means the exit Mach number is 1. Okay, so what it says here, so we have a nozzle, so this inlet of the nozzle is station 4 and exit is 5. So we have been given the stagnation condition at the inlet, stagnation temperature and stagnation pressure 4 bar. Okay, so now when it says that the nozzle operates isentropically, right, we can say that the stagnation temperature and stagnation pressure stays constant. Okay, so the at the exit of the nozzle, the stagnation properties will be same as that at the inlet of the nozzle, right? Okay, and what else is given, this m5 is equal to 1. Okay, So this m5 is equal to 1 means this m5 is this 5 actually corresponds to what we call the star state, star condition, because star conditions is the condition at which the Mach number is equal to 1, right? Okay, so okay, so what we need to find out, first we need to find out the gas temperature at nozzle exit, so T5. Okay, so we need to find out T5. So this ratio T5 by T05 is basically the star, so like T5 is equal to the star condition at state 5, right? So we know that these ratios, the start temperature to stagnation temperature, is given by 2 by gamma plus 1, right? Okay, and so, and remember here in this case the gamma value is 1.333. Okay, so in for this case we can't directly use the uh, this gas table, because this gas table is given for a gamma of 1.4. okay, so this is valid for air, but for this case you can't use the gas table. So you have to also be careful when you are using the gas table and when you are not. So gas tables are generally given for gamma equals to 1.4, so then you can directly use the values from that, but here it's not, you can't do that. Okay, so this, if you do this, so gamma is 1.333 plus 1. okay, so this is 0.8573, so this will give T5 is equal to, you get 850.6644 Kelvin. okay, so this is your T5. all this, so this again to note that this corresponds to the star condition, because the flow Mach number here is 1. okay, so second part B, so to find out the pressure ratio, so P04 by P5. okay, so this we can write P04 is equal to P05, so this is P05 by P5. okay, so this again, so this is the ratio of stagnation pressure to static pressure. okay, at station 5. so this we can write this ratio T05 by T5 whole to the power gamma by gamma minus 1, right? And this we see this value is 1.08573, gamma is 1.333, and this is 0.003. okay, so this ratio will get as 1.8524. okay, then coming to the third part. So third part is we have to find out the nozzle exit area, which is A5, if the mass flow rate is 10.17 kg per second. okay, so given is your m dot is 10.17 kg per second. okay, and we can write m dot is equal to density times area times the velocity, right? So basically A5 will be equal to m dot by rho 5 into V5. okay, alright, so how will you find these values? So so you can find the rho 5 from equation of state. okay, you can find rho 5 is equal to P5 by RT5. okay, so T5 we have computed, and P5 you can compute from this ratio, you know, P04, so from there you can find P5. okay, and V5 is equal to the speed of sound, because gamma T5, because since the flow Mach number is equal to 1. okay, so from there if you can find rho 5 and V5 and m dot value is given, you can get the nozzle exit area A5. okay, so I'm not so this I will solve it, I don't have the answer, so I'm not spending time doing the calculation, but you can do this and get the answer. okay, any questions or doubt in this problem? Yeah, go ahead, Apurv. You can unmute and ask.
So the V5 value, that will be the maximum possible exit velocity, right, for
No,
the
no, no,
nozzle?
no, no, no. It's not that maximum possible exit. So maximum possible exit velocity happens when you, when the maximum velocity possible, when you have a question like find the maximum possible exit velocity. That means that the exit temperature is equal to the static temperature at the exit is equal to 0 Kelvin. Okay, so like I have solved a problem in the last class corresponding to that, you can find that. But here it specifically mentioned that your the exit Mach number is 1. Okay, which means that this your velocity will be equal to the speed of sound. So that's like you can compute it from the square root of gamma RT. Okay, does that answer your question?
So, sir, is that the convention followed that for finding the maximum velocity, the exit velocity and the exit temperature should be 0 Kelvin?
Yes, right.
Is that a
Yes, exactly. So
convention?
like let me just show you how we get it. Okay, let's say you have something like a let's say you have reservoir. Okay, and you put something like a nozzle like this. Okay, so let's say here your stagnation conditions are P0 T0, and let's say your flow is isentropic. Okay, okay. So and here let's say your velocity is okay, so let's see, this is your state point 1 and this is state 2 exit. Okay, so your P01 is equal to P02 is equal to P0, and T01 is equal to T02 is equal to T0. Okay, so this is basically since the flow is isentropic, the stagnation property stays constant. Okay, so now you have to find out V2. Okay, so if you just write the energy equation here, that H1 plus V1 square by 2 Cp is equal to H2 plus V2 square by 2 Cp. Okay, so this is left hand side basically becomes your stagnation enthalpy, right? 2 Cp, sorry, I made a mistake here. This should be
CP won't come, sir.
yeah, no, yeah, if yeah, right, you can just let's say write in terms of temperature, then yeah, then this is right. So yeah, so I'm just writing in terms of yeah, so I'm writing enthalpy in as Cp times temperature. Okay, and then dividing both sides by Cp. Okay, so what we will get here, so this is your T0 and this is T2 plus this thing. Okay, so now what is your expression for velocity? This is 2 Cp times T0 minus T2. Okay, right. Now if you look at the right hand side, okay, so when do you think maximum where temperature maximum velocity will occur? When you have stagnation temperature, sorry, this max V2 is equal to V2 max when T2 is equal to 0, right? So when say a question like what is the maximum velocity you can attain, it means that if you can expand the expand the gas through the nozzle such that at the exit the temperature becomes equal to 0 Kelvin, that is when you will achieve the maximum velocity. Okay, and you can, as you can see, this will like correspond to a Mach number of infinity. Okay, because the speed of sound will be like gamma T2 will be 0, so Mach number will correspond to infinity. That is also an thing, like if the velocity is maximum, which means that Mach number is infinity. Okay, okay, so does this clear your doubt?
Yes, sir.
Okay, thank you. Yeah, but for this problem it's not said that we have to find the maximum velocity or something. Here it's specified that the exit Mach number is equal to 1. Okay, so you can just find the temperature. Okay, and exit Mach number 1 means it is a it is like the state is corresponds to the start state, critical state. So we know what is the temperature ratio, start critical temperature to stagnation temperature ratio in when Mach number is equal to 1. So you use that here and find the temperature, and then we know that the flow velocity is equal to the speed of sound. Okay, and that's how we compute the flow velocity here. All right, any other question? Okay, let's move on then. So Okay, so next thing, the major point of discussions for today's session is related to normal shocks, right? So normal shock, as we have seen, is like a discontinuity in the flow where the flow properties change very rapidly, like there is a jump in flow properties across this normal shock, and this normal shock is very thin, and this thickness is of the order of 10 to the power minus 6 meters. Okay, so this is, you guys see, this is if you know, remember what we call as the free molecular path. Okay, so it's of the order of 2 to 3 free molecular paths. So across a very small region this changes occur. So upstream we represent the properties as p1, t1, m1, u1 and m1, and downstream we have p2, t2, m2, u2, m2. Okay, so like how the properties varies across a normal shock. Okay, so this is for a, what we are saying is a stationary normal shock, because the normal shock is stationary with respect to our laboratory frame of reference. Okay, so we have seen that since this is like the assumption as the flow is adiabatic, right, which implies that the stagnation temperature stays constant. Okay, so there is the shock is a very thin layer, and you can see that there are strong gradients in temperature and pressure exit within the shock wave. Okay, so what else happens is that the shock wave acts like a thermodynamic device which compresses the flow. Okay, so P2 is greater than P1, so what we see, the pressure increases, density also increases, temperature also increases. Okay, so as you can see that the gas, after passing through the normal shock, gets compressed, its pressure, temperature, density is increasing. Okay, its velocity decreases, so u1 is u2 is less than u1. Okay, and m2 is correspondingly, m2 is also less than m1. So upstream Mach number is supersonic, and downstream the flow becomes subsonic. Okay, so m1 is greater than 1 and m2 is less than 1. Okay, so for this, what is the properties for normal shock, and in a normal shock, this as you can see, there is a steep gradient in temperature, pressure and density exits, so there will be a very strong so the effect of viscosity, heat conduction, those effects will be very strong, which, and this presence of gradients induces irreversibilities in the flow, so the flow is not isentropic. Okay, so flow is non-isentropic, which means that there are so the change in entropy can only occur because of irreversibilities, because so the, as we know, entropy change has two parts. One occurs due to the energy transfer, another part due to the irreversibilities or entropy generation. Since here the flow is adiabatic, there is no entropy change because of heat transfer. The only entropy change that can occur are because of the presence of irreversibilities or losses in the flow. So that's how the entropy change occurs, and that's why the entropy change is always positive. So S2 minus S1 is greater than 0. Okay, and so as the flow is non-isentropic, the stagnation pressure will decrease. Okay, and we have seen that there is this expression by which we can say how the stagnation pressure varies, a relation between the ratio of stagnation pressure to the change in entropy. Okay, so we have derived this expression in the last session also, and we have seen that this is valid for an adiabatic quasi 1D adiabatic flow. Okay, so this is also valid for a shock, as has been also derived in the lectures and shown. Okay, all right, so there are different formulas for this we can use. So let me write the main formulas. So so we can represent this temperature and pressure ratios across the shock in terms of the upstream Mach number m1, so and gamma. So some important formulas are there. Is the what is the downstream Mach number m2. So m2 square is given as 1 plus gamma minus 1 by 2 m1 square divided by gamma m1 square minus gamma minus 1 by 2. Okay, this is one formula you can and the pressure ratio P2 by P1, which is given by 1 plus 2 gamma by gamma plus 1 into m1 square minus 1. Okay, and there is a complicated long expression for temperature ratio as well, but there are other ways also you can in which you can find the temperature actually. Okay, the like this one. So once you know the upstream and the downstream Mach number, since the total temperature or stagnation temperature stays constant across the shock, you can also use this expression to find the temperature ratio. Okay, so these are like mainly major three expressions you might need to remember. So first, you given m1, you can find m2 from this, and the pressure ratio from the second expression, and the last expression that I am written, that is basically that is equivalent to writing T01 is equal to T02. So T01 is equal to static temperature times 1 plus gamma minus 1 by 2 m1 square, right? So I have just written the expressions for like the static temperature at stagnation temperature at both upstream and downstream end of the shock in terms of their static temperatures and Mach number. Okay, so these are the major three formulas. Remember how to equate, and we'll also see how we can. There are also gas tables available for this normal shocks for gamma equals to 1.4. So we'll also use that to solve the problems today. Okay, all right. So let's solve the first problem. What we have is a helium which is flowing with a Mach number of 1.8 and it enters the normal shock. We have to find out what is the Mach number downstream of the shock and pressure ratio across the shock. Okay, so since this is helium, actually for helium I forgot to mention the gamma is 1.67. okay, so I have to use the gamma value of 1.67 for this problem. So what is the first, let's find out the Mach number. So m2 square is equal to, what is the formula, 1 plus gamma minus 1 by 2 m1 square divided by gamma m1 square minus gamma minus 1 by 2. Okay, so given m1 is equal to 1.8 and gamma is 1.67. Can you solve this and let me know what is the value of m2 you are getting. One two four into did you compute the value of m2? Yes, so we'll get an value of m2 as 0.41. Okay, okay, all right. So next part we have to find out the pressure ratio across the shock. So the formula for this is P2 by P1 is equal to 1 plus 2 gamma by gamma plus 1 into m1 square minus 1. Okay, 1 plus into 1.67 divided by 1.67 plus 1, and this is 1.80 square minus 1. No, 0.41 is the right answer, I guess. Just recheck once. Just
M2
yes,
square is
sorry, sorry,
for
sorry,
one.
sorry, sorry. You are right. Correct. You are right. M2. Yeah. So M2 square is we are getting 0.41, and M2 are getting, yeah, 0.64. Yeah, yeah. Thanks for correcting this. Okay. All right. So next thing is the yeah, ratio of P2 to P1. What is this value? Okay. Yes, we'll get 3.80. Thanks. Okay. So okay, so this is the first problem. So we just simply applied the formulas to get the downstream Mach number and the pressure ratio across the shock. Okay, all right, let's go to the okay. Before going to the next problem, so let me introduce how the gas tables for normal shocks looks like. Okay, so again we have seen that the major expressions for the normal shock waves, they are given in terms of the upstream Mach number m1 and gamma. Okay, so again we fix gamma at 1.4, that is for layer. So then everything becomes a function of the upstream Mach number. Okay, so this is our upstream Mach number. So and see what given. So based on that we are given the downstream Mach number m2. Okay, we have given the ratio of static pressure ratio across the shock, ratio of static temperature, then we have been given this thing, there is no point giving the ratio, what will be the ratio of total temperatures, that is equal to 1, right, because total temperature stays constant. Then we have delta v by a1. So this delta v is basically what is the change in velocity normalized by the speed of sound upstream of the shock wave. Then we have the ratio of total pressure. Okay, and this should be always be less than 1 because total pressure decreases across the shock. And we also have the ratio of total pressure at the downstream of the shock divided to the static pressure at the upstream end. Okay, so these are the values generally given for a normal shock table. So again this table is taken from this book, and that's the PDF I have uploaded in the Google Drive link. Okay, and you can use that. Okay, okay, so next problem we'll try to solve using the gas tables. Okay, okay, so let's go through the problem. So we have a normal shock that stands in a duct. The fluid is air, which may be considered as an ideal gas. So remember, all the formulas I have derived is based on the assumption that the fluid is an calorically perfect gas. That's why you can make the simplification and come to the final expressions. Okay, so that assumption is important. So the properties upstream of the shock are given. So we have a shock wave. So T1 is equal to 5 degree centigrade, which is 278 Kelvin. P1 is 65 kilopascal, and V1 is 668 meter per second. Okay, so we have to find out the static temperature and pressure downstream of the shock, which means T2 and P2. Total temperature and pressure downstream of the shock, which means T02 and P02. Entropy change across the shock, which is S2 minus S1. And we have to show this, how this process on a TS diagram. Okay, so to use the gas table, we need M1, because M1 is the independent parameter across with all the gas tables quantities are listed. Okay, so first we need to find A1. So A1 is equal to square root of gamma R T1, 1.4 into 287 into T1 is 278. So A1 you will get 334 meter per second. Then comes M1. So M1 is 668 divided by 334, which gives us the Mach number is 2.0. Okay, so now we can find the values. Okay, so all right, so first point is we have to find out the static temperature and static pressure downstream of the shock. Okay, so for this we need this ratio T2 by T1 and P2 by P1. Okay, so let's go to the gas table. Okay, so I have this gas table PDF open. Okay, so our upstream Mach number is 2. Okay, sorry, so this is not the normal gas table, so this is the normal shock table. Okay, I guess this is visible. So first we have to look at the row where the upstream Mach number is 2. Okay, so we are yeah, so T2 by T1 is 4.5. Sorry, no, make a mistake. Yeah, sorry, I have to look into this, right? So T2 by T1 is 1.6875, 1.6875, and P2 by P1 is 4.5. From where did you get these values, Harshit? Did you compute it, calculate it? If you calculate, just check the calculations. So okay, so again, so we are looking at this column. Okay, this one. Okay, yeah. All right, looking at this row. So for M1 of 2, we need the first the 4.5 is the ratio of static pressure, and 1.6875 is the ratio of static temperature. Okay, so for the T2 becomes 1.6875 into T1. So T1 is 278, so we'll get T2 as 1.6875 into 278, 469.125 Kelvin, and P2 will be equals to 4.5 into, what is the pressure, 65. So 4.5 into 65, V2 will be 292.5 kilopascal, right? Yeah, just check the calculate like values carefully. Okay, so this two, like, do the calculation carefully. So ideally you shouldn't get this much of a difference, but yeah, well, I like here, like, don't ignore much significant digits while doing the calculation. Okay, all right. So okay, so this part is done, first part is done. So second part is we have to find out the total temperature and total pressure downstream of the shock. Okay, so first is the total temperature. Okay, so we know that T02 is equal to T01, right? Why? Because mm, uh, because it's like the flow is adiabatic across the shock, right? Okay, so let's say if we want to find T01. Okay, so what we can do here is, like, we can do two things. We can do we can find this ratio T01 by T1. What, how, where we can get that? So so T01 by T1 is this thing, right? 1 plus gamma minus 1 by 2 m1 square. Okay, so this we can get from gas table again. So now we have to look at the isentropic gas table. Okay, so here again, okay, this row. So here we see that here basically T by T0 is given. Or we get T1 by T01 is equal to the value 0.55556 0.55556 from gas table at m1 equals to 2.0. Okay, yeah, again, as I said, you can directly compute it, or like, so I'm trying to, like, today I'm like trying to explain how to use gas tables to solve these problems. Okay, but you can also, like, directly apply the formulas here and do that. Okay, so what we'll get as T2 T01 we'll get T01 is approximately equals to 500.40 Kelvin. So T02 is also equal to 500.40 Kelvin. Okay, all right. Okay, so again again you could have, like, taken the ratio of T02 to T2 at the Mach number of M2, like, and also you should have gotten the same answer. Okay, so, like, you can also use T02 by T2 is equal to 1 plus gamma minus 1 by 2 M2 square. Okay, so since you know M2, so if you put in the values, you should also get the same T0, so you should again get the same answer. Okay, okay, all right. Okay, so what is next we need to find out is what else, what the total pressure downstream of the shock, right? So stagnation pressure downstream of the shock, so P02 by P1. Okay, so this ratio you can get again from the okay, let's first find P01. Okay, sorry, let's just wait. So from gas table, P0, sorry, P1 by P01 is equal to, So you see P1 by P01 is equal to this value, okay, 0.12780, 0.12780 at Mach number of 2.0. okay, so from this we will get P01 as, what was P1, 65 kilopascal, so P01 you will get yeah, 509 kilopascal. Okay, now from normal shock table for M1 equals to 2.0 you will get a value of this P02 by P01. So we are going to the normal shock table again. Yeah, so yeah, so you see P2 by P0 0.72087 is 0.72087, so P02 will be equal to 0.72087 into 5. What, did I make a mistake? What we are getting? 6, yeah, 367. Okay, fine. What happened? Yeah, into 509, so P02 comes out as, yeah, 367 kilopascal. Okay, all right. Okay, so yeah, so this in case you don't remember the formulas in any case, so this is how you can solve using the gas tables. Okay, otherwise you can just, as you know, you can just put in the actual values and you can find that. Okay, so like the formulas and get the expressions. Any questions so far? Okay, let's move on then. So part C is we have to find out the entropy change across the shock. So entropy change, so S2 minus S1. So here you can do two things. We can apply this formula that we know entropy change equals Cp ln T2 by T1 minus R ln P2 by P1. Okay, so we know all the values of the values of the static temperature and static pressure at both upstream and downstream of the shock, so you can put the values here and get that. Okay, another formula is you can use this, or we know that P02 by P01 is equal to e to the power minus delta S by R. So from that you can get P delta S or S2 minus S1 is equal to minus R ln P02 by P01. Okay, so so this is like a better formula to use in these cases, because this is like will like save the computation time compared to this one. Okay, all right, so you can, let's go with this formula, the second one. Yeah, delta S. Harshit, you, when you do all this, also remember to mention the units. Okay, so what you are getting is right. Yeah, 93.9 joule per kg Kelvin, or 0.0939 kilojoule per kg Kelvin. Okay, all right. Okay, so I hope this is clear. So we have the last part where you need to like show this on a TS diagram. Okay, so let's do that. So So this is our TS diagram. First is our state point 1. Okay, so this is our T1, and we have the pressure isocontour going through this, which is at P1. Okay, so corresponding to this we can draw the stagnation state here. So this is this is the state point 1. So this is state 01, the corresponding stagnation state, right? And so the pressure isocontour goes through here is the P01. Okay, all right. So this is T01, and that is also equal to T02. So T02 will lie that the 02 state point will lie somewhere on this horizontal state line. Okay, all right. So what happens in the, so where will the state point 2 lie? We know temperature and pressure both, temperature increases in the shock wave and across the shock wave, right? And entropy also increases. So it will be in the like you have to go towards the top on the right, yeah, top right. Okay, so let's say we take just, it's just an approximation. So let's say this is our point 2. Okay, so point 2, so this will be our P2. Okay, so you see automatically we get P2 is greater than P1 because the the isocontour corresponding to P2 is lying over P1, so that is greater than, so P2 is greater than P1. Okay, now the corresponding stagnation state, so you have to lie on this horizontal red line so that T2 is equal to T02. Okay, so this is our 02 state. So this will be our P02 isocontour. Again, P02 isocontour is lying lower than P01 isocontour, as so that is, we know that when entropy increases, the stagnation pressure decreases. Okay, so this is the thing, and we can just draw the state point something like this. So this is the shock. Okay, so like this is how the change in state point occurs across the shock from 1 to 2. Okay, all right. And so this is, we see that S2 minus S1, right, is equal to, so we have is equal to also S02 minus S01, right? So if you see, if you like project the state points onto the horizontal axis, so you can see that the S2 minus S1, that difference is equal to S02 minus S01. So S02 minus S01, if you can write in this way, that CPln T02 by T01 minus RLN P02 by P01. Okay, and this will go to 0, right, because T02 is equal to T01. There also you will get the same, like that expression you use. Okay, so from the graphically also we showed that this change in entropy is equal to minus RLN P02 minus P02 by P01. Okay, is this clear? Any questions? Okay, great, let's move on. Okay, question 4. Air has a temperature of 300 Kelvin and 2 bar, which and is at 2 bar absolute pressure. It is flowing with a velocity of 868 meter per second and enters a standing normal shock. What is the percentage of compression done by the normal shock to the flow? Okay, so what, like compression, when we mean compression, we generally means indicate the density ratio, right? So percentage of compression is generally represented by this del rho by rho 1 into 100. This is what we need to find out. Okay, so for that first we need to find out again the flow Mach number. First we find out A1, which is gamma R T1. So again let me draw the schematic. So we have a shock, normal shock. T1 is equal to 300 Kelvin, P1 is equal to 2 bar, and velocity U1 is equal to 868 meter per second. Can anyone compute and tell me what is the value of M1? Yeah, okay, thank you. So M1 we are getting as 2.5. okay, so what we need to find out is delta pro by rho 1, right? So delta p by rho 1 is like this is rho 2 minus rho 1 by rho 1, or rho 2 minus rho 1 minus 1. Okay, so we need to find out this. So for that we need to find out rho 2 minus rho 1, rho 2 by rho 1, the ratio of rho 2 by rho 1. So this, so what is rho 2? Rho 2 is P2 by RT2, rho 1 is P2 by RT1. So what this gives us is basically we need this ratio P2 by P1 into T1 by T2, or P2 by P1 divided by T2 by T1, right? So we can get this from this, get T2 by T1 and P2 by P1 from normal so we can use again, go back to the normal shock gas table to find these values. Okay, so let's, so what is the upstream Mach number? 2.5, right? So yeah, so we need to look at this line. Okay, so our P2 by P1 is 7.125 and T2 by T1 is 2.1375. okay, so P2 by P1 is 7.125 and T2 by T1 is 2.1375. okay, so then rho 2 by rho 1 becomes 7.125 divided by, okay, yeah, so this will get around 3.33. okay, right? So finally then percent compression, that will be equal to delta rho by rho 1 into 100. So that is, we have seen rho 2 by rho 1 minus 1 into 100. So this is 2 how much will you get it? 2.33 into 100, right? So 233%. yeah, 233.33%. yeah. All right, so this is the percentage compression. Yeah, right. Okay, so I guess this is clear. Okay, so we have seen we can directly get the temperature and pressure ratios from the gas table, or we have formulas for that, and the density ratio we can compute from that. Okay, All right, let's move on to the next problem. What happened? Okay, the question is, a blunt nosed missile is flying at a Mach number of 2 at standard sea level. Calculate the temperature and pressure at the nose of the missile. So how will we proceed with this problem?
Stagnation conditions.
Yes, right. Okay, but one thing, we cannot use a stagnation condition directly corresponding to Mach 2.0. Okay, because, so let's say we have, so this is given, we have a blunt shaped body. So when you have a blunt shaped body and the free stream Mach number approaching it is equal to and supersonic, right? So we'll get a bow shock. Okay, so we get a bow shock. Okay, so yes, so if anyone remembers that we did a similar problem like that in the previous session. So we had an aircraft flying at a Mach number, and we had to find out the pressure at the pressure and temperature at the nose of the aircraft. Okay, but in that case the speed was subsonic. Okay, so if the speed is subsonic, there is be no shock. So the we can get the stagnation condition corresponding to that Mach number will, the subsonic Mach number will be the temperature and pressure at the nose. Okay, but here we have a supersonic flow and a blunt object. Okay, so blunt object here is important because that's why we are getting a bow shaped a bow shock like this. Okay, and this part, small part of the bow shock, this we can treat as a normal shock. Okay, so like the so here, from here, so the then the that we need to find out the temperature and pressure here at this point. So here this be equal to the is a stagnation point, which implies that temperature and pressure will be equal to stagnation values. Okay, all right. So here the thing is, there's another thing, the assumption here is that the at the just at the across the shock the flow is non-isentropic, as we know, but in other parts of the region the flow is isentropic. Okay, because that's why, like, from the downstream of the shock to this point to the nose of the missile, the stagnation property stays constant. Okay, right. So need to do first, we compute what is, so this is 1 and this is 2. So first we need to compute what is T0 T01, right? So T01, so we can get this ratio, right? T1 by, sorry, again let's go to the isentropic gas table. Okay, so from here we know this value, this yeah, so T by static to stagnation temperature, that value is 0.55556. so 0.55556, so that's why we get T01 is equal to, what is the value, we get 15 is 15 plus 273, so 288 by 0.55556, 5118.4 Kelvin. Okay, all right, and P1 divided by P01, again go back to the gas table, that is 2780. Okay, again all this is from gas table at corresponding to M1 equals to 2.0. So P01 you will get 101325 divided by 0.12780, 792.840 kilopascal. Okay, so at nose we need to find out, so T02, that will be equal to T01 equals to 518.4 Kelvin, right, because stagnation temperature stays constant, so the value will be same, but P02 by P01, that we need to find out. So there is a like but the stagnation pressure will decreases across the shock. So P02 by P01, this ratio we can find out from the normal shock table again. Okay, so that value is this one, 0.72087, 0.72087 from normal shock table. Okay, right, so if in let's say if you don't do shock table, so what you have to do, first you have to find out the yeah, so first you have to find out what is the static temp, so we will know the stagnation temperature, then you can find out the static static temperature. Okay, so from the stagnation to static temperature ratio at both 1 and 2, you can find out the stagnation pressures at each of these location and then take the ratio. Okay, and there might be some simpler way to do this also, but like using the gas table makes it simpler. Okay, so P02 will be equal to 0.72087 into 792.84 kilopascal. So P02 will be equal to 571.534 kilopascal. Okay, is this clear? Okay. Okay. So the important thing is here is you have to realize that there will be a shock forming. Okay, so if you just compute the stagnation properties corresponding to Mach 2 without ignoring the formation of shock, you will get the pressure value wrong, right? Okay, so you have to understand that there will be a shock will be forming. Okay, so that's why and take the properties downstream of the shock. Okay, any questions? Okay, good. Okay, all right, so next problem. So consider a point in the supersonic flow where the static pressure is 0.4 mm atmosphere. When a pitot tube is inserted in the flow at this point, the pressure measured by the pitot tube is 3 atmosphere. Okay, so to find out the what is the Mach number of and the flow velocity at this point. Okay, all right. So it's said here that this is a supersonic flow. Okay, so when you insert a pitot tube in a supersonic flow, let's say, what will happen again, we will get a shock like this, okay, no shock. So we are basically measuring the stagnation pressure. So what is measured here is the stagnation pressure downstream of the shock, okay. So basically we can say if this is 1 and this is 2, so we know P02 is equal to 3 atmosphere, okay. so so this is and at state point 1, so as you know in this kind of arrangement, so P2 is we know is P2 is used to measure the flow velocity, right. So we have seen in incompressible flow it is very simple, the stagnation pressure is, we assume that is equal to P plus half rho V square, and we can directly do that. And but if the flow is not incompressible but subsonic, we have seen we have to use the stagnation pressure ratio that we get in terms of Mach number to get the, that is what we call is the compressible pitot. But now this is supersonic pitot tube, so we have a Mach normal shock forming, and the stagnation pressure that we are measuring is the what happens downstream of the shock, okay. And upstream here we will generally have one more manometer that measures the pressure to be 4.4 atm. So P1 is equal to 0.4 atm, okay. So this ratio P02 by P1, so that is 3 by 0.4, that is equal to 7.5, okay. So what now we need to compute the Mach number, okay. So let's, without using any formula, let's go to the gas table, okay. So in the gas table you will see there is this parameter given, the stagnation temperature downstream of the shock divided by the static temperature upstream of the shock, okay. That is what we have computed, that is we have found to be 7.5, okay. So let's look at this column where we get 7.5, okay. So we are getting 7.5, so we are not getting exactly 7.5, but you can say that this will lie somewhere between these two values, okay. Harshit, you are computing using formulas, okay, you can also do that. So but like let's go by the gas table. So if you see here, it is will come, so this PT2 by PT1, this value will approximately come in between 2.33 and 2.34, okay. So let's okay, so oh sorry, what did you say, 2 point we are getting 7.5, right. So if you interpolate, you should get the value between 2.33 and 2.34, right, because the, you see this bit, the 7.5 occurs between 2.33 and 2.34, okay. So just if you interpolate, just do the interpolation correctly, okay. So but so from, just let's say from gas table, so the approximate value of M1 we are getting, so I'm just doing some, let's say I'm just doing some slight approximation, let's say it's between 2.34 and 2.33 and 2.34, let's assume it's 2.335, okay. So this is our Mach number, upstream Mach number, okay. So and we have been asked to also find out the flow velocity, okay. So in the problem temperature is not given, let I just mention static temperature in the flow be 300 Kelvin, okay. So if that's the case, the velocity u1 will be equal to 2.335 into gamma RT, okay. So this will give the value of u1, okay. Is this clear? So use of gas tables in normal shocks problem is very useful, because it's like in this kind of when you don't need to apply and memorize this complicated formulas. Okay, is this clear, light? Any questions or doubt? Okay, cool. Okay, so I'm just, this is a simple calculation computing the velocity. You can do that. I will give the final answer while I will upload the final PDF, but you can get the answer easily. Okay, so the second part of the problem is to compute the entropy rise caused due to the shock that forms in front of the pitot tube. Okay, so we need to find out delta S, and that we know is minus R ln P02 by P01. Okay, so we know that, again we come back to here. So P02 by P01, so this is the second last column, the sixth column. Okay, so again we can interpolate the values, or you can just make an approximation. Okay, let me just take the values at 2.33. okay, so P02 by P01 is equal to 0.57 at M1 is equal to 2.33 from gas table. Okay, so minus 287. Yeah, we, sorry, what you are saying? Yeah, P0, yeah, we don't need to find out P01 and PZ uh, 02 separately here. Okay, because what you are interested in the ratio. Okay, so this is 0.15. so when someone tell me what is the value you get. Where you are getting this value of P01? Yeah, okay, you can computed that from the ratio. Yeah, okay, yeah, so but yeah, so this will get 161.2 joule per kg Kelvin. Okay, right. Okay, so far good. Any questions, doubts? Okay, I hope this is clear. Yes, yes, you can unmute and ask. Yes, yeah, sure.
Yes, sir. Good evening, sir.
Yeah, good evening. Yeah, go ahead.
Yes, sir. Pitot tube actually it is measure velocity or stagnation pressure.
So pitot tube is like what? Pitot tube is what is like you put a probe in just against the flow, and this is connected to a manometer, and you know manometer measures the pressure, right? So pressure, so when you put a
Yes.
manometer like this, like let's say normal to the flow, let's say this vertical one, it that will measure the static pressure. Okay, but when you put a pitot tube is when you put the this tube just against the flow. Okay, so what will happen where the when this so just at the this nose of the pitot tube, right there, the
Mm-hmm.
it will measure the pressure there. So what will be the pressure? That is the pressure is the stagnation pressure, right? So then this is connected to a manometer like this, and from the, as you know from basic fluid mechanics, the this difference in the levels of mercury will use to get the pressure. Okay, so from
Mm-hmm.
that pressure we get the based on the what the assumption we impose on the flow, whether it's incompressible or compressible and subsonic, or
Compressible.
compressible or supersonic, we can get the flow velocity. Okay, but it measures the pressure, but the idea of using the pitot tube is to measure the velocity actually. Okay,
Okay,
so if you
that
remember,
means
yeah,
the Petro tubes actually measures the stagnation pressure, and in the
right,
process
yeah,
we
right, we
can
can
calculate
calculate the pressure, yeah,
velocity.
right. So based on the assumption, so when you have done basic fluid
Mhm,
dynamics, the Bernoulli's equation, you remember, you will let's
mhm,
say it's incompressible, there won't be a shock, so you apply Bernoulli's equation between point 1 and point 2. So at point 1 you have
mhm,
so there is no contribution from the potential energy. So at point 1 you have P1 plus half rho v square, v1 square, and at P2
mhm.
you have just P2, right? So that P2 is what is measuring, and
Yes.
P2 is the stagnation pressure. Okay, so you know P2
Mm,
from the P dot 2 measurement, and P1 is from some other manometer, the static measure. So when you equate, you get the velocity. Okay, similarly, like when
mm.
it's subsonic, the flow is subsonic, so then you have to use the ratio of stagnation to static pressure in terms of the Mach number, that
Mark number, yeah.
yeah, right, 1 plus,
Isentropic. Okay.
right, exactly, that assumption. And when you have supersonic flow, you have the shock, so you have to take into consideration of that. Okay, here.
Yes, sir. That
Okay,
means it actually senses the stagnation pressure,
right,
and
exactly,
using some equation we can calculate the
right,
velocity.
exactly, using the
Okay.
like the as what using the way our idea about the how the flow is, so you can use the get the this thing, yeah,
Yes,
okay.
sir.
Okay, and
So,
like also
let's say
like,
someone asks,
yeah, go ahead.
okay, sir. If someone asks what pitot tube measures what, so we should say first we should say the it measures the stagnation pressure,
Right, express stagnation
and
pressure.
right,
Right,
right. Yes, sir.
right,
Okay,
right, yeah.
okay, okay. Clear, sir. Clear.
Mm,
Thank you.
yeah. Okay, let's go to the next problem, question 7. So a gas flow with a velocity of 400 meter per second and a specific volume of 1.1 meter cube per kg. So let's write this. Is passes through a normal shock. So a normal shock, U1 is 400 meter per second. V1, this is a specific volume, this is 1.11 meter cube per kg. And if the specific volume behind the shock is 0.333 meter cube per kg, we have to find out the pressure increase across the shock. Okay, so means we need to find out P2 minus P1. So how will we go ahead with this problem? Any idea, anyone? Yes, right. So you have to refer to the Hugoniot equation. We also don't need to go to the Hugoniot equation here. Okay, so we can just simply apply the what we call our control volume analysis. Okay, so this is our 1, this is 2, and we know the values. Okay, so what we know is, first we know the mass balance or continuity, that is rho 1 u1 is equal to rho 2 u2. So here the density is not given, so everything is terms in terms of specific volume, so we can write u1 by v1 is equal to u2 by v2. Okay, all right. Next we have the momentum balance. So as we know, the momentum balance for 1D flows is given by P1 plus rho U1 square is equal to P2 plus rho U2 square. Okay, so we are interested in P2 minus P1. So P2 minus P1 is equal to rho, sorry, rho 1 rho 2. Doing it right. Yeah. Okay, so P2 minus P1 is equal to rho 1 u1 square minus rho 2 u2 square. So this is u1 square by v1, sorry, minus u2 square by v2. Okay, so we have been given so this is the equation we need. Okay, so just remember that we are not invoking anything about the what we know about the normal shock equations or all. It's just simple application of momentum balance and this thing. Okay, okay, and mass balance. Okay, so we don't know u2, so u2 you can replace from the continuity equation. So u2 is equal to v2 by v1 u1, right? So v2 by v1 u1 square. Okay, so what will we get here? Get u1 square 1 by v1 minus what we are getting here, so v2 by v1 square. Is it right? Yeah, okay. So what else we can do? No, sorry, this will be, yeah, okay. So now we can do this 1 by v1 square, this will be v1 minus v2, right? So I'm just being the denominator, making the denominator v1 square. Okay, so I have to insert a slide. Okay, so finally we will get this expression p2 minus p1 by v2 minus v1 is equal to minus u1 by v1 whole square. Okay, okay, so as we have seen in the Hugoniot equation, right? Hugoniot equation basically relates the upstream and the downstream properties of the shock in terms of thermodynamic quantities only. So it eliminates, so as we know, it eliminates the, it does no velocity or Mach number comes in there. Okay, so and you get a curve like this P and V. So this is your Hugoniot curve. Okay, so wherever, let's say, given and one upstream condition P1 and V1. Okay, so these basically, this, as you see, this equation is like a equation of the straight line approximation between 2 points, right? And okay, so yeah, right. So then this equation gives like a straight line equation between this 0.1 and 0.2 basically. Okay, so this is the upstream location of the shock and 2 is the downstream location. All right, so let's say next we okay, so now if we what we need to find out, this one p2 minus p1 is v2 minus v1 into e1 by v1 square. Okay, so now all the values are, we know, v2 v1 u1 is known. So if you put this, we'll get p2 minus p1 as 100.9 kilopascal. Okay, all right, is this clear? Okay, so this is just, we didn't have to actually invoke the Hugoniot equation. We could just took the mass balance and the momentum balance, okay, and just some manipulation we got the answer. Okay, so always just sometimes always we, when we see a problem, we think that in which formula should we fit in there, but at times it's just application of the simple basic fundamental understanding of the problem: momentum balance, mass balance, energy balance. Yeah, and even the, as we know, the shock expression that we get, that we arrive from finally using the these three balance equations only, right? Okay, all right, let's move on. Okay, so now question 8. So this is on, now we'll move on to, we have done some problems on normal standing normal shocks. Now next problem is on a moving normal shock. Okay, so we see here there is a, let me draw a schematic of this. So we have a shock which is moving with a speed of w, which is 600 meter per second, into a region where air is at 300 Kelvin and 0.7 atmosphere and is flowing with a velocity of 100 meter per second. Okay, so let's say this is our region 1. So this is flowing with a velocity of 100 meter per second in this direction. Okay, and here the temperature is 300 Kelvin and the pressure is 0.7 atmosphere. Okay, so we have to find out in the region behind the moving shock. Okay, just let's ignore this line. You have to find out the static temperature and pressure behind the moving shock. So to find out the static temperature and pressure in region 2, okay, and the flow velocity in the region behind the moving shock. So the, let's say this, so as we have seen that when the shock moves, it induces some more velocity. So we have to find out what is the flow velocity behind the shock and the stagnation temperature in both the flow regions. Okay, so let's start. So how do we solve the problem? What we do is we change the frame of reference so that our standing shock, so this moving shock becomes a standing shock, and we attach, that means we attach the frame of reference to be moving with the shock. Okay, so if we do that, let's say now our shock is stationary. So this is, let's say, our state point 1 prime and this is state point 2 prime. Okay, so here now the here the velocity is u1 prime. Let's say this is moving in opposite direction. What will be the velocity? So to keep the make the shock stationary, we have to apply minus w in the left direction. So this u1 will be 500 meter per second. What will be t1 prime and p1 prime? This will be same, right? Because these are static properties and this does not depend on the frame of reference, right? This will be same as this. Okay, so now shock is stationary and u2 prime will be this. Okay, so first let's say find out what is our a1 prime. a1 prime is gamma t1 prime, and so a1 and a1 prime will be same because our t prime and t1 prime is same, because the static properties in one region does not get affected by the change of the frame of reference, right? So this a1 you will get as 347.19 meter per second. All right, and the Mach number, remember we are using m1 prime here, so this is the Mach number in the changed in the frame of reference when the frame of reference is attached to the shock. Okay, so this is now a standing shock. Okay, so our m1 prime will become 500 divided by a1 prime, so this is 1.44. all right, uh, 441, is this right? Let's see. So then we have to go to this find T2 prime and T1 prime. So T2 prime by T1 prime, this ratio, and P2 prime by P1 prime, this ratio we can find from the normal shock table. Okay, so we have Mach number of 1.44. Let's go to the normal shock table. Okay, so P2 by P1 is, and T2 by T1 is 1.28. This is 1.28, 066, and P2 by P1 is 2.25253. So from there we get T2 prime is equal to 1.8 times 300, sorry, 1.28, yeah, we are getting 384. Actually you check the values once. Okay, so T2 is equal to 384.20 Kelvin. Yeah, okay, be careful while making the this translation. Okay, and the Kelvin values. Okay, so and P2 prime will come out as 1.577 ATM. Okay, so this is our P2, 1.577 ATM. All right. Okay, so is this clear? So we have found out the static temperature in these regions. Okay, so let's move on to the next part. We have to find out the flow velocity in the region behind the shock wave. Okay, so part A is done. Part B, so first we need to find out what is the u2 prime. Okay, so what is the velocity u2 prime? So u2 prime will be equal to m2 prime into gamma r t2. So m2 prime is, again if you look at the shock table, m2 prime is 0.72345. okay, 2345 from shock table. Okay, and this is 1.4 into 287 into T2 is 384.2. so u2 prime will get as 284 meter per second. Okay, so now tell me what is the value of up. So the flow velocity, now we have to get the yeah. So what will be the value of up, the flow velocity behind the moving shock? Yeah, so basically what we need to do is, need to do 600 minus u2 prime. So we will get a 316 meter per second. Yeah, all right. I think it was 284.25. so we'll get 315.75. okay, is this clear? So you have this, like, be careful about while making the transformations, okay, because like the coordinate like the changing the frame of reference, okay. And remember that the static property stays constant, but the stagnation properties will doesn't stay constant here, okay, because the stagnation, remember when we do stagnation properties we add static properties plus velocity let's say we want to compute stagnation temperature, we do static temperature plus velocity square by 2 cp, okay. So when we do the change in reference we are subtracting some velocity, right? So doing the square of that and doing the square of actual velocity, that is, so in the change frame of like in the actual frame of reference the stagnation temperature will not stay constant here because the flow is unsteady here, okay. So stagnation temperature stays constant only when we have a steady and stationary shock, okay. So you need to keep that in mind. Anyways, any questions or doubt? It's clear? Okay, so here we change the frame of reference such that shock becomes stationary, okay. So and again when you do that be careful of the signs of the velocity that you are using, okay, and the signs and the subtraction or addition thing, okay. All right, okay. And again always note that the when there is a moving shock, okay, so this again since the shock has to this W will be greater than A1, okay. So W, because the speed of the shock wave is always greater than the speed of the sound wave in the region in which it is moving, okay. That's then only the shock wave can travel. Okay, so like we'll do more problems on moving shock in the next week because moving shock is a important thing in shock tube. So in the next lecture content when we'll discuss about shock tubes and how it operates in the, so shock tube is a very important experimental setup in the context of studying compressible flows, okay, mainly supersonic flows. So we'll see how a shock wave is generated there, basically a moving shock wave generated and reflected. So we'll do more problems on this moving shock wave in the next class, okay. So I think in this session I have two more questions, so this will be like MCQ type questions, okay, to test your understanding of the fundamental understanding about the shocks, okay. All right, so let's move on. So question 9, which of the statements is correct? So let's go one by one. I will want you guys to answer whether it's right or wrong, so true or false. So first statement 9a, total enthalpy stays constant for all normal shock. Is this true or false? Yeah, so this is, we remember this is actually not correct, okay. So a total enthalpy or what we say stagnation enthalpy stays constant only for steady or standing shock, standing normal shock, okay. Oh, all right, so I forgot, so in this part there is one more question, so part B is done. So part C, there was we have to compute the stagnation temperature in both the flow regions. Okay, sorry I missed that part. This will actually clarify this. Sorry, I missed doing this. So part C, so T1, sorry T01 is equal to T1 plus E1 square by 2 Cp, and T02 is equal to T2 plus UP square by 2 Cp. Okay, can anyone compute both these values and tell what are the values here? So what was T1? 300 plus U1 was 100 square by, and T2 was 384.20 plus 315.75 whole square by 2 into 5. Okay, so like if you just look at the values only, you will understand that T02 is greater than T01. Okay, okay, so you see that the static temperature is larger in T2, and also the your velocity is higher. Okay, so you can see T02 is greater than T01. Okay, so coming to the next question, we have seen that the total temperature can only stay constant when total enthalpy or total temperature will stay constant only if we have a standing normal shock. Okay, this is not valid if the flow is unsteady or or for unsteady flows. If the shock is, like in this case it is an unsteady flow because the shock is moving. Okay, is this clear? Any questions? Remember when we derive that, do the balance, that h1 plus half v square is equal to h2 plus half v square, that energy balance, that is the steady state steady flow energy equation. Okay, and from that we get that total total in stagnation enthalpy or total enthalpy staying constant. Okay, but here we have an unsteady flow when the shock is moving, so that's why we cannot directly apply that in the, yes, so in that context. All right, so there is an important point: in case of moving shock, the total enthalpy and stagnation enthalpy does not stay constant. Okay, so when you do the this when you do the change in transfer, do the change in the frame of reference while solving problem for moving shock and use the normal shock gas table, you can only use the relations corresponding to the static temperatures. Okay, let me go to the gas table. So you see in the gas table you have these different columns. So ideally when you will do the transformation, like when you are solving a moving shock problem and you do the change the frame of reference so that the moving shock becomes stationary, and you get, then you can and you get a standing normal shock, then you can only use this you can use this fast like the first four columns: m2 p2 by p1, t2 by t1, and delta v by a1. Okay, but you cannot use this, actually the ratios of stagnation temperatures and stagnation pressure to static pressure. So these last two columns are not valid for moving shocks. Okay, all right, when the quantities involving the stagnation properties. Okay, so we have to be careful about that. Okay, okay, so the first statement is false, the which means that total enthalpy will stay constant only in case of standing normal shocks. All right, moving on, next statement B: the value of A star stays constant across a normal standing shock. Okay, yeah, so this is true because we have a standing normal shock means a steady flow and the flow is adiabatic. Okay, so if the flow is adiabatic, A star stays constant. Okay, so that because the A star value we obtain by going to an hypothetical reference state where the Mach number is 1, and we do by applying the steady state steady flow energy balance equation. Okay, and if the in between 2 points if it is steady flow and the flow is adiabatic between two, and there is no heat transfer or work transfer happening between two state points, the value of A star will stay constant. Okay, next 9c, the Hugoniot equation is not valid for real gases and chemically reacting flows. Is this true or false? Yes, this is false, because when Hugoniot equation is derived, so this basically we just do some manipulation taking the energy balance equation, momentum balance equation, and mass balance equations, right, for 1D flows, and do some manipulation to get that. So that basically relates the relates the properties upstream and the downstream of the shock purely in terms of thermodynamic variables. Okay, it does not involve any velocity or Mach number. Okay, or we also don't invoke any assumption related to the whether the gas is calorically perfect or ideal, right? So we don't invoke the equation of state or anything. So that's why the Hugoniot equation is also valid for chemically reacting flows and real gases. Okay, let's say from, if you have heard of detonation wave, which is like a shock wave in a chemically reacting flow, so that is, so Hugoniot equation is also valid in that cases. Okay, okay, so then last part, the last question, normal shock can produce a maximum percentage compression of 83.33% in air. What will be this? So the question is, what is the maximum compression it can produce? Okay, so we know that when what is the maximum dense, so compression is what we know, this delta rho by rho 1, right, which is rho 2 by rho 1 minus 1. So what is max rho 2 by rho 1? So we have seen that max rho 2 by rho 1 is tends to 6, right, in the when this Mach number tends to infinity, right? Yeah, so what will be the actual value then? So delta rho by rho 1 will be actually equal to 500%, right? So this is false. Okay, so are all the statements clear? Okay,
Sir, maximum should be 600, no?
no, we were no, this is rho 2 minus we need to, percentage compression is delta rho by rho 1, so we have to do rho 2 minus rho 1 minus 1, like.
Okay, but sir, maximum, the ratio can be 6, right, sir?
No, the maximum percentage compression. So if you remember, we did this problem in the previous thing, like in one of the problems we discussed what this yeah, maximum like percentage of compression is given by this delta rho by rho 1. Okay, so you have to do delta rho by rho 1, so that is, so that is rho 2 minus rho 1 by rho 1, which is rho 2 minus rho 2 rho 2 divided by rho 1 minus 1, so it will be 6 minus 1 into 100. Okay,
Okay, sir.
yeah, so let's say I'm defining here the percentage compression as delta rho by rho 1. Okay, So you also have a problem on this in the assignment, I guess, where you have to find the percentage of compression that is defined in this way. So change like the, this is like the change, like the relate, like the percent change in the density, percent change in density. Yeah, go ahead.
But sir, but in the previous question where you are showing,
Yeah, right.
can you go back to that slide, sir?
This one, sorry, this one.
No, no, no. Ah, yes, yes.
Yeah,
Here they have asked what is the percentage of compression done by a normal shock wave corresponding to the 2.5 Mach number.
right, exactly.
But in that case, they have asked the what is the maximum percentage of compression we can obtain when Mach number is infinite,
Yeah, right, right,
tending to the very high magnitude.
right,
So it
exactly.
should be 6, sir, I think.
No, see, we have to find out this quantity, this delta rho by rho 1. What will be delta rho by rho 1? Just a second.
That should be, in that case it will be 5.
Yes, right, that's what I said, that delta rho by rho 1 is the percentage compression achieved. That is what I am getting, like this one. So second. So delta rho by rho 1, that is rho 2 by rho 1 minus 1, right? That is 5. So the percentage compression will be delta rho by rho 1 into 100 is 500%. Okay, now it's clear or still?
Okay, that means
So
maximum density change can
yeah,
happen to the
yeah, so
magnitude of
500%, yeah, right. So you are, what we are saying, yeah, this is in AR. So AR, so like that's why, so AR only, AR means gamma equals to 1.4, and for that we have seen that when the like when Mach number tends to infinity, our mm, the this ratio rho 2 by rho 1 tends to 6, right? And what
yes,
then, what is the
yes.
percent, like this percentage compression, what is the percent change in the density that is getting attained? Okay, so like the definition of percentage compression is this delta rho by rho 1.
Okay,
Okay,
okay.
now it's clear, I guess.
At a maximum, we can get a 500%,
Yeah, in
and the
500%
ratio we can get
yeah,
a
ratio is 6.
6.
It's like, so it's saying the maximum we can get 500% increase in the density because of the while when air passes through the shock.
Air is passes. Okay,
Right,
okay,
okay, yeah,
okay.
okay, yeah,
Got it.
yeah, okay. So now we're asking her to find the star part again. Okay, so how
Thank you.
the, yeah, thank you. So how the star properties are derived? If you remember, the star properties are derived from, let's say we have a state point, we go to an hypothetical state point from that state through an adiabatic process such that the flow Mach number becomes 1, right? So that correspond to the star state. Okay, so so to get the one second. Okay, so start state, let's say we have one uh, so in start state we have H star plus uh, V 2. Okay, now this V star is equal to now gamma R. Okay, let's just, okay, now and if we now write this in terms of temperature, okay, now the thing is V star is equal, so this is what is, this is like an adiabatic process, right? Because there is no heat transfer happening. Okay, so now V star we know is given by gamma T star. Okay, so like the stagnation state and start state are like reference states corresponding to a given state point. So in stagnation state, what I was saying, we are, let's say we take the fluid at a temperature at a given state point to a state where the flow velocity is 0. Okay, so and the start state, when we are saying the start state is a reference state where the flow velocity is equal to the uh, speed of sound. Sorry, this is, I did something wrong here. This should be gamma t. Okay, so so that the at the start state the flow velocity is equal to the speed of sound. Okay, so that is the reference. Okay, so and and so when we are doing this, we are saying that the deriving the start, like the start temperature. So this gives us a start temperature, and A star is basically equal to gamma r T star. Okay, so when the flow is adiabatic, okay, the T star reference, just like remember when we said the flow is adiabatic, the stagnation temperature doesn't change, right? Because there is no heat addition to the process. Okay, and the stagnation state is derived with the stagnation temperature, that is derived based on the assumption that it is adiabatic. Okay, similarly the start temperature is derived based on the assumption that the temperature state, that is derived based on the assumption that we are going through an hypothetical adiabatic process. Okay, so if the flow is adiabatic, the start temperature will not change, and if start temperature does not change, the A star will also not change. Okay, if the flow is adiabatic. Does that answer your question? Yeah, okay, yeah, all right, yeah. So this is like think that this is equivalent to our stagnation temperature only. So this is the stagnation, again the stagnation state and the your start state are like thermodynamically equivalent reference state. Okay, so like we do express this, we do derive these stagnation properties or star properties, because in some cases it's easy to express the quantities in terms of star or stagnation properties. Okay, as we have seen. Okay, so and the start temperature and start temperature and stagnation temperature both are derived, the value of them are derived based on the condition that the flow, that it is adiabatic. Okay, so if the flow stays adiabatic, okay, so the starts, let's say you have the flow is going from station 1 to station 2. So the start state at station 1 and the start state at station 2, both are like this star and stagnation states are defined only at the corresponding state points. Okay, okay, but now if the flow stays adiabatic, the star and the stagnation properties at both these states point will be the same. Okay, so again I will repeat like what I did again in the previous class. When the flow is adiabatic, your stagnation temperature stays constant, your start temperature stays constant, since your uh, the star speed of sound, what is A star, that, or what we call the characteristic speed of sound, that depend on T star. Since T star stays constant in adiabatic flow, A star will also stay constant in an adiabatic flow. Okay, now if there is some heat transfer or heat loss happens, so all this will change. Okay, now in addition to that, when we impose the condition that the flow is isentropic, which means that is adiabatic plus it's reversible, in those cases we say that the stagnation pressure will stay constant, the star pressure will also stay constant. Okay, but if the flow is adiabatic but not reversible, body reversible, then the flow becomes isentropic. Okay, in that case the stagnation pressure and star pressure will change. Okay, so that's as we have seen in case of shock, it is adiabatic, total temperature is staying constant, but total pressure is decreasing, all right, because of the irreversibilities. Okay, any other doubt? Yeah, Apur, go ahead.
So it's from lecture number 18.
What is it
In
about?
that,
Or just what is the content of the lecture? This.
sir, it is about weak shock limits, sir.
Yeah.
In that lecture, firstly, strong shock limit was discussed, and just before Hugonio relations,
Yeah. Right.
weak
Right.
shock relation
Right.
was
Right. Go
discussed.
ahead. Yeah. Go ahead.
And yes, sir, in that there's one long expression delta
Hmm.
s by r.
Hmm.
It was inside one logarithmic expression was there with three brackets.
Hmm.
So, like I tried expanding it, but I'm getting the final expression I'm getting in terms of m square. So I just wanted to confirm from you.
I haven't checked the lecture. So like the idea is like, so you will get an expansion. So when you expand this, you will get an expansion in terms of powers of m. Okay.
Yes, sir,
So
yes, sir.
so the idea is like, if like when this the, or like this is like terms of the m is the upstream Mach number. So when you
Hmm.
will just this tends to 1, so ideally this will go to this, the change in entropy will go to 0. Okay, so if you also look at
Hmm.
the, and also the this the, that is the weak shock limit. So if you also look at, let's say, the this shock table, right? So when you will see this, so this so if the entropy change in entropy goes to 0, which means the total pressure will also stay constant, right? So if you see the
Hmm.
upstream, like let's say you look at the these first 5 Mach numbers, you see here that the change, the ratio of the total pressure is almost close to 1 here. So this is what you are getting, seeing is the exactly the weak shock limit. So if the total ratio of total pressure is 1, your change in entropy is almost 0, right? Is 0, right?
Yes, sir. But the thing is,
Yes,
either it is
so you're
in
not,
the
what your point is, you are not able to get the expression that professor noted down in the lectures, right?
yes, sir. Yes, 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 sir.
Okay,
I'm
okay.
getting in terms of m square, but m square also, if m is tending to zero, delta s will be zero.
No,
That
no,
is okay. But
no.
yes,
There.
sir.
Okay. I need to check that. Maybe you can check this. I don't know where he did this. So maybe this weak shock limit and strong shock limit will be there in the book by Anderson, or you can refer to this book. Just check there once. This is also a good book. You can refer to this one, Zucker and Bloods. This book you can refer to that. I think it might be there. I am not certain about the derivation now. Okay, if you don't get it, maybe ask me again, or I will derive it in the in
So
the next session.
I'll post on the forum. I'll post my solution on the forum.
Okay,
Maybe.
okay. Yeah, do that. I will check. Okay, all right.
Yes, sir.
Okay, okay. Anything else? Okay, so. mm then let's end the session today. Thank you all for attending. So I will meet you again next week on Fridays. So then there will doing problems related to shock tubes. So shock which will we that will involve doing more problems related to moving shocks and reflected shocks, and also expansion waves. So we'll look into that in the next session. Okay, and if you have any doubts or anything, you can post it in the discussion forum. So, and if something is there, I can also solve those in the sessions next week. Okay, and I guess you had some problem with the typo in the assignment 3, that is resolved, and so you can now get the solutions for that and submit the assignment. Okay, all right, then let's end the session. Good night and have a good weekend. Bye.
Thanks, sir.
Yeah, thank you.